Hello everyone, welcome back to my channel. In this section, we shall see the solution of the total differential equations by the method of grouping. In the last class, we have solved some problems on the TDE by the method of treating one of the variable as a constant. But in this section, we shall solve by using the method of grouping the terms. Verify the condition for integrability and solve 2x square plus 2xy plus 2xz square plus 1 dx plus dy plus 2z dz equals to 0. So in this we group the terms such that it can be easily integrable, and also even this can be solved by using one of the variable as a constant. That is, in this case we can choose this x as constant, then we get dx equals to 0, and we can proceed the same procedure as we done in the last video. But here we use the method of grouping the terms, so that will be easy than the method of that is treating the one of the variable as a constant. Okay, here first we write the given equation: 2x square 2xy 2xz square plus 1 dx plus dy plus 2z dz equals to 0. This is our given PDE. Now writing p terms, q terms and r terms, we get p is equals to 2x square plus 2xy plus 2xz square plus 1. This is our p, and q value is the coefficient of z, y is 1 and r is given by 2z. Now differentiating this p with respect to y, that is dou p divided by dou y we get. So this is totally x terms, so it contains y terms also. So 2x being constant, y differentiation 1, and here again so it is treated as constant, so its differentiation is 2x. Now dou p divided by dou z, differentiating with respect to z, it contains only one term, so that is 2x is taken constant, and z square differentiation is 2z, which is equals to 2 into 2 4x into z. Now dou q divided by dou x is equals to 0, and dou q divided by dou z is also equals to 0 because it is constant. Now dou r divided by dou x, differentiating with respect to x we get 0, and differentiating with respect to y also we get 0. Now we write the condition for integrability. The condition for integrability is p into dou q divided by dou z minus dou r divided by dou y plus q into dou r divided by dou x minus dou p divided by dou z plus r into dou p divided by dou y minus dou q divided by dou x equals to 0. Now we consider the LHS part. Substitute the values of p, dou q, all the derivatives. So p value is 2x square plus 2xy plus 2xz square plus 1 into dou q by dou z. Dou q by dou z is equals to 0, and dou r by dou y is also equals to 0 plus q. Q value is 1, dou r by dou x. Dou r by dou x is 0 minus dou p by dou z. Dou p by dou z is 4xz plus r value. R is 2z into dou p by dou y. Dou p by dou y is dou p by dou y is 2x minus next dou q by dou x. So dou q by dou x is 0. So further simplifying this term becomes 0 minus 4xz. Now multiplying these two we get 2 into 2 4xz. These two get cancels, we get 0, which is equals to RHS part. Hence the condition for integrability is satisfied as the given TDE is integrable. So integrable means we can find the solution here. Okay, so next, to find the solution, we write the given equation as, that is the grouping the terms. We use the method of grouping the terms. So grouping the terms, we get, so here you can observe that in this in these three terms I take 2x as common. 2x on taking common, we get x plus here y plus we get z square, and this one I separate this with this terms, that is we write dx plus 1 dx, remaining terms as it is 2z dz equals to 0. Now grouping the terms, we get like this, or it can be written as 2x into x plus y plus z square dx. So you can observe that it is dx dy z 2z. 2z can be written as differentiation of z square, because differentiation of z square is 2z. Therefore, so on grouping these three terms, we can write it as, it is the differentiation of x plus y plus z square, right? So on simplifying this, we get dx plus dy plus 2z means it is differentiation of z square is equals to 2z into dz. So now dividing throughout the equation, by this term, that is x plus y plus z square. On dividing throughout this equation, we get 2x, this to get cancels, dx plus here d divided that is d of x plus y plus z square divided by x plus y plus z square equals to 0. Don't cancel these two because it is a differentiation of this one. Now on integrating, we get 2x integration is 2x square divided by 2 plus, it is of the form f of x, f dash of x divided by f of x, so that we get log of x plus y, it is in the form of 1 divided by x form. Okay, so 1 divided by x into dx form. So therefore its integration is log of x plus y plus z square, that is log of x, equals to, here integration of constant we take it as log c. Further simplifying, we get x square plus, or you can write it as 2 to get cancels, x square equals to, we write it as log c minus log of x plus y plus z square. So simplify, we get, so it can be written as c divided by x plus y plus z square, it is x square, or taking, it is log of, taking anti-log on both sides, we get e raised to x square is equals to c divided by x plus y plus z square, or we can write it as x plus y plus z square equals to c divided by e raised to x square, or it can be further written as x plus y plus z square equals to c into e raised to minus x square. So this is the required solution. Okay. Next problem, verify the condition for integrability and solve yz dx plus 2xz dy minus 3xy dz equals to 0. First we shall verify the condition for integrability. The given equation is yz dx plus 2xz dy minus 3xy dz equals to 0. So here given that comparing with the standard TDE, we get p value is equals to yz, q value is equals to 2xz, and r value is equals to minus 3xy. Now differentiating partially all this with respect to x, y, z, we get dou p divided by dou y. So we don't need dou p by dou x. So simply directly we differentiate dou p by dou y. Okay, with respect to y, its differentiation will be z. And similarly dou p by dou z will be y. And dou q divided by dou x value. Differentiating with respect to x, we get 2z being constant, x differentiation is 1. Next, dou q divided by dou z. Its differentiation will be 2x. Z differentiation is 1. And dou r divided by dou x is equals to minus 3y, and dou r divided by dou y is equals to minus 3x. So these are the partial derivatives. Now substituting all these values in the condition of integrability, that is we have the condition for integrability is p into dou q divided by dou z minus dou r divided by dou y plus q into dou r divided by dou x minus dou p divided by dou z plus r into dou p divided by dou y minus dou q divided by dou x equals to 0. Now substituting all these values, we get LHS equals to p is yz dou q by dou z. Dou q by dou z value is 2x minus dou r by dou y. Dou r by dou y value is minus 3x. Minus into minus, we get plus 3x plus q value is 2x into z. Dou r by dou x is minus 3y minus dou p by dou z. Dou p by dou z is minus, that is y. So we get minus y. R value is minus 3xy. So directly we write minus 3xy into dou p by dou y. Dou p by dou y is z. Dou q by dou x is 2z. So that we get minus 2z. Now simplifying this, we get 2x plus 3x is equals to 5x, 5xyz. Here we get minus 4y, minus 4 into 2 equals to minus 8xzy. Here z minus 2z equals to, we get minus z, minus into minus plus 3 into xyz. You can observe that 5 plus 3 equals to 8 plus 8xyz minus 8xyz cancels, so that we get 0, which is RHS side. Hence condition of integrability is satisfied, that is given TDE is integrable. Okay, now we find the solution of this one. To find the solution, we consider the given equation. It is yz into dx plus 2xz dy minus 3xy dz equals to 0. Here no need to arrange the terms because it is already in the arranging. Okay, so it is already arranged. So simply we divide the whole equation. Okay, dividing throughout the equation by x into y into z, we get, on dividing by x, y, z, yz get cancels, we get dx divided by x plus, here xz get cancels, we get 2 divided by y into dy minus 3xy xy get cancels, we get 3 divided by z into dz equals to 0. On simply integrating we get, integrating we get log x plus 2 taken outside log y minus 3 taken outside log z, and integration of constant is taken as log c, or this can be further written as log c log y. So this, by using the properties of log, we can write it as log of y square minus, it can be written as log of z cube equals to log c, or log m plus log n, we can write it as log c into y square. And similarly, taking this term to the RHS side, it becomes plus, again we apply the log m plus log n, it will be, here it is x, we get log c into z cube, or it can be written as x y square equals to c into z cube. So this is the required solution. So like this we can solve any problem. Next problem, verify the condition for integrability and solve x z cube dx minus z dy plus 2y dz equals to 0. First we shall verify the condition for integrability. So from the given, comparing the given equation with the standard TDE, we get p is equals to x z cube, q equals to minus z r equals to 2y. Okay, now dou p divided by dou y is equals to 0, dou p divided by dou z equals to x taken outside z cube differentiation is 3z square, and dou q divided by dou x equals to 0, and dou q divided by dou y is equals to 0. Dou r divided by dou x is equals to, we get 0. Dou r divided by, here we have to find dou q divided by dou z. Dou q by dou z value is equals to minus 1, and here dou r divided by dou y is equals to 2. Okay, now we verify the condition for integrability. For that we have to substitute all these values in the condition for integrability. So that is, the condition for integrability is p into dou q divided by dou y minus dou r divided by, it is dou z, dou r divided by dou y, plus q into dou r divided by dou x minus dou p divided by dou z, plus r into dou p divided by dou y minus dou q divided by dou x equals to 0. Now substituting values in the LHS side, p value is x z cube dou q by dou z. Dou q by dou z value, dou q by dou z is minus 1, minus dou r divided by dou y is 2, plus q is minus z, dou r by dou x is 0, minus dou p by dou z is 3xz square, plus r value is 2y, dou p by dou y is 0, minus dou q by dou x is also 0. Simplifying all these terms, we get, here we get minus 3, so it is minus 3xz cube, minus into minus plus 3xz cube, here we get 0, so these two get cancels, we get 0. This is the RHS side, hence the given TDE is integrable. Now to find the solution, first we write the given equation. Given equation is, it is x z cube dx minus z dy plus 2y dz equals to 0. Now dividing throughout this equation, by z cube, we get x dx minus, dividing by z cube, we get dy divided by z square plus 2y divided by z cube into dz equals to 0, or it can be written as x dx. Here we take minus sign outside so that it can be written as 1 divided by z square into dy minus, it can be now it can be written as 2y, or it can be written as 2 divided by z cube into y into dz equals to 0. Now you can observe that here 1 by z square as it is, y differentiation is dy. Next, y as it is, 1 by z square differentiation is 2 divided by z cube. So it is minus 2 divided by z cube. So that this can be written as, we can replace it by x dx as it is, minus sign as it is. This can be written as differentiation of y into 1 divided by z square, or simply y divided by z square equals to 0. Okay, so you treat this as here differentiation of y into 1 by z square. Applying UV rule, it is equals to y as it is, differentiation of 1 by z square is minus 2 divided by z cube dz plus, now 1 by z square as it is, y differentiation is dy. So you can observe these two equals to, that is, this one is equals to this one. Therefore we can replace this term by differentiation of y divided by z square, or y into 1 by z square, both are same. Now simply integrating on both sides, we get x, integration is x square divided by 2 minus, here differentiation get cancels, we get y divided by z square equals to, integration constant we take it as c, or it can be further written as, we can take 2 z square as a LCM, so that we get x square z square minus 2y equals to c, or it can be further written as x square z square minus 2y equals to 2c z square. So this is the final answer.